Hey everyone, we'll see, last time we were talking about the dot product, right? So that was an operation. If you have two vectors, you do this operation with the two vectors, it creates a number. That number was called the dot product. Today we're going to talk about another operation that can be performed with vectors, but it only works with vectors in R3, right? So three-dimensional vectors. So we need a couple of vectors, so let's let A be the vector A1, A2, A3, and B is the vector B1, B2, B3. Now we're going to define what's called the cross product. So the cross product of A with B is, and we write it A and then a little times symbol in between. So A cross B is the way you would read this, not A times B, A cross B. And in this case, so remember when we did the dot product of two vectors was a number. This is going to be a vector. So the cross product of two vectors is a vector. And the formula is fairly complicated looking. So it goes like this. So A2 B3 minus A3 B2. That's the first entry, the first component of a vector. The next one is going to be A3 B1, B1 minus A1 B3. And then the last entry is going to be A1 B2 minus A2 B1. Okay, so when you have two vectors in R3, you take the cross product, you get a vector in R3, and it's this complicated looking formula. If you notice, I had to look at my notes to actually compute that, right? I do not have this formula memorized. I never have, and I never will. And the reason, right, although I can compute a cross product quickly, and you will be able to too, I recommend don't bother memorizing this formula. Recognize that there is such a formula. We're going to come up with a computational tool that will allow us to compute the cross product without having to memorize this formula. Okay? But so at this point, I mean, fine, right? I mean, here's two vectors. Take this thing called the cross product. It creates this complicated looking formula. Now we need to figure out, why would you ever want to compute such a thing? Like, what's the point? Right? And also, we want to figure out a quicker way, a more intuitive way to compute this. So that's our next step. And in fact, let's put it over here. So to learn this method of computing determinants without memorizing that, cross products, without memorizing this formula, we need to know about determinants. If you've ever studied matrices before in some other class, you've already probably learned what a determinant is. I'm going to go through all the steps here. So first of all, there is what's called a 2x2 determinant. And determinant. And so if you have four numbers arranged in a square-like fashion, so arranged in a square like this, you can take what's called the determinant of those numbers, and the computation is A times D minus B times C, right? That is called the determinant of this square arrangement of numbers, called an array or a matrix of numbers. Okay, so to compute it, you can think of it sort of diagonal-wise. So you take A times D, and then you subtract, right, the product on the other diagonal. So there's two diagonals. Take the first diagonal, subtract the result of multiplying against along the second diagonal. Right, that's called a 2x2 determinant. Now there's a 3x3 determinant. I wish I wouldn't have erased that, but that's all right. To compute a 3x3 determinant, you need to know how to compute a 2x2 determinant. And so let's set up now A, B, C, D, E, F, G, H, I. So now if we have 9 numbers arranged in a square-like fashion like this, the 3 by 3 determinant is computed as follows. So I'm going to look at A. I'm going to do A times the determinant of the 2 by 2 that I get by deleting the column and the row that contain A, right? So if you were to delete the column and the row that contain A, you're left with this little square down on the right-hand side, and so we compute the 2 by 2 determinant of that one. Then we subtract minus B, right? So let me clean up my picture now. So now what I want to do is I want the 2 by 2 that we get by deleting the column and the row that contain B. So that's going to be B times the determinant of DFGI plus, okay, and then we're going to do this one more time with C, right? So delete the row and the column that contains C. We're left with this little square right there, so it'll be plus C times the determinant of DEGH, right? So this thing right here, this is called a 3 by 3 determinant. One thing to be aware of, it alternates sign, positive A, negative B, positive C. Okay. So in each case then, when you grind this out, you'll get a number that's called the determinant of this 3 by 3 matrix or 3 by 3 array of numbers there. Okay, so determinant is a number that you get when you arrange a bunch of numbers in a square. So determinants are useful if you go on to linear algebra, either Math 244 or Math 206. You're going to use determinants quite a bit. Now we're going to see why we need them for this class right now. So if A is the vector A1, A2, A3, and B is the vector B1, B2, B3, then what I would like to do is I'm going to create a matrix, a 3 by 3 matrix, where in the top entry I put the vectors I, J, and K. So that's our top row. In the second row, I'm going to put A1, A2, A3. And in the third row, I'm going to put B1, B2, B3. And now what I'd like to do is take the determinant of this one right here. So let's see, it's going to be I times the determinant of that lower right-hand corner. So that's going to be an A2, B3 minus A3, B2. So that's going to be times I. I'm gonna arrange it in this because I'm running out of room here. So plus, okay, so now it's going to be J. Sorry, it's not going to be J. It's going to be minus J. Remember, for a 3 by 3, you reverse the sign of the middle term, and so that will be A1, B3 minus A3, B1. That's times J. Plus, now it's going to be K times the determinant of the lower left-hand 2 by 2. So that will be A1, B2 minus A2, B1. That's times K. Now, what this gave us here is a vector, and I'd like to write this now in angle bracket form. It's going to be, for the I component, that's going to be an A2, B3 minus A3, B2. The next one, all right, I got a minus sign. I'm going to factor this minus sign, or, feed the minus sign through, and so it'll give me A3, B1 minus A1, B3. And then in the third entry, that's an A1, B2 minus A2, B1. And now if you notice, right, take a look at the formula I first gave you. right? This is exactly what I wrote. Sorry. That's exactly what I wrote down when I wrote down the definition of the cross product of A and B. And so, I'm going to put some exclamation marks there. What we have then is that A cross B is equal to the determinant of the 3 by 3 you get from putting I, J, K in the top, A1, A2, A3 in the second row, and B1, B2, B3 in the third row, right? And so this is why I've never memorized the formula for a cross product, because I can compute a determinant very quickly, very easily, and so I use this determinant formula, right? I know the determinant formula, that allows me to compute cross products. Okay, so let's do an example here. So let's say A is the vector 1, 2, minus 3, and B is the vector 0, 1, minus, let's do minus, okay. How about 0, minus 2, positive 1? And what I'd like to do is compute A cross B. Okay, and I'm going to use this formula up here, so I'm going to put an I, J, and K in the top. Then we'll have 1, 2, minus 3. And then we'll have 0, minus 2, 1. Now I'm going to do this example slowly, but in practice, when I compute a determinant, I don't even write this stuff down. I write my vectors like this, and I can compute it just by using the vector form. So once you've done a little bit of practice, you don't want to have to write this I, J, K stuff down, right? You should be able to, just by writing down the vectors, right, compute determinants in your head and write down who the cross product is, right? So the cross product is not a process, it's not a lengthy process, right? Once you get used to this, or once you're familiar with it, it's actually quick and easy to compute a cross product. Okay, but we'll do it slow this time. So let's see. First, it's going to be the I component. So that's going to be 2 minus 6. Right? So that will be a negative 4 times I. Then we do minus, and so it's going to be 1 minus 0. So that will be minus 1 times J, plus negative 2 minus 0, so that'll be plus minus 2 times K, which I prefer to write it in angle bracket form, so that would be a negative 4, negative 1, negative 2. Okay, so this vector right here, this is the cross product. This is A cross B. So let's try another example, and I'll do this one without writing out the matrix, just so you can see how it goes, right? And with some practice, right? It's okay if you always want to write the matrix, it's fine, right? But you should see that it's not, or hopefully you believe that it's really not that time-consuming of a process to compute a cross product. So let's say A equals 4, 1, minus 1, and B equals 3, minus 1, 2. So here's the idea now, and I'm going to go straight to angle bracket notation. That's typically what I do. So imagine, right, there's really an imaginary I, J, and K up here. And so for the first entry, it's going to be 2 minus 1. So we get a 1. In the second entry, 4 times 2 is 8, minus a negative 3, so that's plus 3. 8 plus 3 is 11. Remember to reverse the sign in the middle, so that's minus 11. And then we'll get a negative 4 minus 3, so that gives me a negative 7. 4. Okay, so what you see then is it's actually pretty quick to compute a determinant once you're used to the process, right? So practice, start off by doing it this way. In your homework, you're going to have problems that ask you to compute the cross product. Start off doing it this way, and once you get the idea, hopefully you can move to this setting right here, where you can go straight from here to the angle bracket notation for the cross product of A cross B. Now, here's what I want to do. So, I would like to look at my first example. So in the first example, here's what I want to look at. I'd like to look at A dot A cross B. Okay, so A, that was 1, 2, minus 3. And A cross B is right here, so minus 4, minus 1, minus 2, minus 4, minus 1, minus 2. And so let's see what happens. So it'll be a minus 4, minus 2, so that's negative 6 plus 6. We get 0. Also, let's look at what happens if we do B dot A cross B. All right, so that would be a 0, minus 2, and 1, dot negative 4, negative 1, negative 2. So what does that give me? It gives me 0 plus 2 minus 2. It gives me 0 also. Now, last time what we recognized is that when you get a dot product equal to 0, what do we say about the vectors? We say they're orthogonal. So what you want to notice from this first example, A is orthogonal to A cross B, and B is orthogonal to A cross B. Let's look at the second example. So we're still in this observation. In the second example, let's not write it all out, but if I do A dot A cross B, so let's see, I'm going to do the dot product, this vector with this vector. That's going to be 4 minus 11 plus 7. That's 0. And if I do B dot A cross B, 3 plus 11 is positive 14 minus 14 is also equal to 0. So in the second example, what we should notice, or what we see, is that A is orthogonal to the cross product and B is orthogonal to the cross product. And these are not coincidences. That's the point. All right? We have this complicated looking formula for this thing called the cross product. Why do we have this formula? What is the whole reason for doing this? The cross product creates a new vector, right? You start off with two vectors and it creates a new vector that is orthogonal to both of the ones that you started with. That's the point. So we're going to write that as a theorem, right? It is always true that A cross B is orthogonal to both A and to B. The picture is something like this, right? So here's the vector A, here's the vector B, and so A cross B forms a right angle with both vectors. Right? And you could actually prove this. Just crank it out from the formula and you'll see it's always true. If you have a vector A and a vector B, you'll get a vector A cross B that's orthogonal to both. Now, if you have two vectors, so let me see, I got pens here. Let me use pens. So let's say you have a couple of vectors, right? So these pens represent vectors. Okay. Now, no matter how I hold them, right, or how I squeeze them together, put them there, if I hold these two vectors, I can ask the question, how many vectors are orthogonal to both of these? Well, let me grab another pen here. This one is orthogonal to both. So is this one that's a little bit longer. Longer. And so are the ones down here. So when you have two vectors, there are actually an infinite number of vectors that are orthogonal to the original two, right? This one, and then any scalar multiple of this one is also orthogonal. So fine, all right, the cross product creates a vector that's orthogonal to both of your original vectors, and now the question is, which one, right? Of the infinite number of vectors that are orthogonal to original A and B, which one is the cross product? Okay, so that's what we want to answer next. The first thing, so if you notice how I drew A cross B, and I mean, I had to draw this on a chalkboard, so I have 2 dimensions, but I really wanted to represent this in 3 dimensions. Now, okay, so you don't need to write this down, but let's say I have an A and a B, and they really live in the plane that the chalkboard is in, right? So that these really, here's a plane, the chalkboard is a plane, and imagine that A and B, instead of trying to get some perspective or some depth perception or whatever, they live in A and B both live in that chalkboard. The cross product satisfies what's called the right-hand rule. You've probably heard this before. Here's how it works. If we want to talk about A cross B satisfies the right-hand rule in the following sense. What you do is you take your hand, your fingers, and line them up, point them in the direction of A, and then curl them in the direction of B. And when you do that, your thumb will be pointing in the direction of A cross B. Use your right hand to do, I should have said that. Use your right hand to do this. So take the fingers of your right hand, point in the direction of A, curl them in the direction of B, and your thumb will be pointing in the direction of A cross B. Right? So anytime if you have 2 vectors, there are 2 orthogonal directions. There's the up, the out of the board direction, and then there's the into the board direction. So if I do A cross B, then the written as I have it right here, then the cross product will be coming out of the board, right? So that gives us our direction. Remember that a vector is defined by both a magnitude and a direction. So right now we know the direction, and we still need the magnitude. And by the way, notice, if I reverse this, so if this vector was A and this vector was B, and now I want to compute A cross B. All right, so I need to put my hands in the direction of A in such a way that I can curl my fingers in the direction of B. Notice my thumb will now be pointing into the board. So if you reverse the direction of A cross B, then the direction, right, the right-hand rule will tell me that it points in the opposite direction. Okay, so first let's write this down. So A cross B satisfies the right hand rule. Okay, so that tells us the direction. Now we need magnitude. And this next theorem is going to tell us the magnitude. So it goes like this. If theta is the angle between A and B, then the magnitude of the cross product is equal to the magnitude of A times the magnitude of B times the sine of the angle between them. Okay, so this gives us sort of a geometric characterization of the magnitude of the cross product right here. And we're going to get an even better interpretation in just a second. But one thing to notice, so this will be a corollary, it's a consequence of the previous theorem. Two vectors are parallel if they're scalar multiples of each other, right? So meaning I consider those two vectors to be parallel, they're pointing the same direction. And I also consider these two vectors to be parallel, they're pointing in opposite directions, right? So if one vector is a scalar multiple of the other, then they're parallel. Now, if two vectors are parallel, that means that the angle between them is either 0 or it's pi, right? If they're pointing in the same direction, the angle's 0, otherwise the angle's pi. And notice, if we come back to this equation right here, when theta is equal to either 0 or pi, sine of theta is equal to 0, which means the right-hand side is equal to 0, which means the left-hand side is equal to 0. And so what we have as a corollary is that I guess I need to say non-zero, right? Yeah, non-zero vectors, A and B, are parallel if and only if the magnitude of their cross product is equal to 0. Now, okay, so what do we have now? The cross product is a vector that's orthogonal to both A and B, satisfying the right-hand rule, and also satisfying this geometric picture, or this geometric formula, but I want to make it even more geometric, and so I'll just write this as a fact. You can do a little bit of trig to verify this. If I take the vectors, let's say A and B, and I line up another copy, another representation of B that starts at the tip of A, so there's another version of B, and then I take a version of A lined up at the tip of B, what we get is a parallelogram. And it turns out that, you can just do a little bit of trig to verify this. There's theta. All right, if you want to compute the area of this parallelogram, it would be the length of B times the length of this. And it turns out, just doing some trig, right, that this is length of A times sine of theta. Which means that the area of this parallelogram is length of A times length of B times sine theta, which is exactly equal to, right, the magnitude of the cross product. So the fact, the area, or let's say it like this, the magnitude of A cross B is the area of the parallelogram determined by A and B. All right, so this gives us a nice and completely geometric characterization of the cross product. A cross B is the vector that is orthogonal to both A and B, that obeys the right-hand rule, so that tells us the direction, whose magnitude is equal to the area of the parallelogram determined by the two vectors. All right, so that's a nice characterization of the cross product. So let's do an example or two here. So so let's find a vector orthogonal to the plane containing the following points. So it's going to containing the point 1, 1, 1, 1, 2, minus 1, and minus 1, 0, 4. Okay. So probably you've heard this at some point that a plane is, as long as you've got 3 points that are not on the same line, right, then determine a plane. And so what we want is the plane determined by those 3 points. Well, we don't want the plane, we want a vector orthogonal to that plane. So let me just draw a little schematic here. Here's my 3 points, 1, 1, 1, 1, 2, minus 1, and minus 1, 0, 4. So there's a plane that contains those 3 points. We want a vector that's orthogonal to that plane. And here's the idea. With those 3 points, we can create 2 vectors, call them A and B. And once we have those 2 vectors, right, I can create A cross B. A cross B, if I use the right-hand rule, right, A cross B will be pointing into the that way, right? But it will be orthogonal to both A and B, which means it will be orthogonal to the plane that contains those vectors. Okay, so who's A? A is going to be the vector, so remember it's head minus tail, so it'll be a 0, 2 minus 1 is 1, minus 1 minus 1 is minus 2. And then B is the vector minus 1 minus 1 is minus 2, 0, so that'll be a negative 1. And then 4 minus 1 is 3. So now A cross B, that's going to be 3 minus 2. That's 1. 0 minus 4 is negative 4, but remember to reverse the sign for the middle term. And then it'll be 0 minus negative 2, so it'll be positive 2. Just checking to make sure I did my computation right by making sure that it's orthogonal. So in my head, I'm going to compute, well, let's just do it. So check the dot product. So that's a 0, 4, minus 4 is 0. And then we get negative 2 minus 4 is negative 6, plus 3 gives us 6, right? So there's the cross product. This vector, which will be pointing that way into the board, by the way I drew this, right, is orthogonal to both of A and B, which means it's orthogonal to the plane that contains those 3 points. Another example, so let's find the area of the triangle containing those same 3 points there. So containing, or I should say with vertices. Area of the triangle with vertices 1, 1, 1, 1, 2, minus 1, and minus 1, 0, 4. So it's basically the same picture here, right? Except, right, we've got a third leg of the triangle, right? And we would like to find the area. And here's the idea, right? A triangle, right? Let me redraw the picture here, right? A triangle is exactly half of a parallelogram. And so if we knew the area of the parallelogram determined by those 2 vectors, so here's an A and a B, right? Divide it in half, right? That'll give us the area of the triangle. Well, the area of the parallelogram is going to be the magnitude of that vector, and so the area of the triangle will be 1/2 the magnitude of A cross B. So to compute this, we just do magnitude of A cross B over 2. So that's going to be, so it'll be a 1 plus 16 plus 4 over 2, which is square root of 21, so root 21 over 2. One last thing Oh, actually, let me say two separate things. So one thing to notice, the cross product is not commutative, right? The dot product is. It doesn't matter. You can do A dot B or B dot A and you get the same answer. The cross product is not the same. And here's the reason, right? If you do A cross B versus B cross A, right, you're going to have to flip your hand over, right? So A cross B and B cross A, they point in opposite directions. So here's a fact, right? They are negatives of each other. So B cross A is equal to minus A cross B, right? It's a scalar multiple. It's just a vector that points in the opposite direction, right? Same length. And then one last thing. So given vectors A, B, and C, their scalar triple product is A dot B cross C. And it turns out it doesn't matter what order you do this in. Right? It's the same as A cross B dot C. You can put them in whatever order you like. But geometrically, the absolute value, so notice you're taking a dot product, right? So this gives us a number. Geometrically, right, there's an interpretation for the absolute value of this. And so here's how this goes. If you take A, B, and C and have them all emanating, let's see if I can draw this, have them all emanating from the same point, what you get is a bunch of parallelograms. So let's see if I can draw this picture here. So let's say A, B, and C. So this object right here, determined by the three vectors, right? It's a bunch. It's a solid object. It's not quite a cube, right? What it has is sides that are parallelograms, right? It's called a parallel piped, right? So this is the parallel piped, determined by A, B, and C, and it turns out that this parallel piped has volume exactly equal to the absolute value of the scalar triple product. So this parallel piped has a volume equal to absolute value of A dot B cross C. So that's a good place to leave off. I think there's a homework or two that asks you to compute volumes of parallel pipeds. And so you just compute the scalar triple product and then take the absolute value. Okay, so we will see you next time.